Okay, today's lesson is 60. What's our title? Get ready?
60.
60. Our objective is area of a parallelogram. What's our objective? Get ready?
Area of a parallelogram.
Excellent. Today we're going to learn the formula for the area of a parallelogram. It will be reviewed for somebody because you did learn it in course 1 and course 2. But today what's new is we're going to graph it, we're going to dilate it and make it bigger and find the new area of the dilated image. So, first recall, in a rectangle you've got a length and a width. We could also call it base and height. Notice that in a rectangle the height is perpendicular. If we were to inscribe a triangle inside of a rectangle, the triangle would meet somewhere up on the top, so the height of the triangle is really the perpendicular height where it meets up with the base. I like to explain it by having a person standing on top of the triangle, dropping a rock. If the rock drops, it's going to drop vertical and meet perpendicular to the base. So that's the height. That's how tall or how high my triangle is. Why is that important? Because in a parallelogram, this is not the height of the parallelogram. The height is the vertical height or the perpendicular height. So if you were a person here and you dropped a rock right there, that is your height. So be careful. Don't use the diagonal slant length right there as your height. And this is the base is regular. So let's talk about, before we talk about the formula, I like to show the formula and introduce it with a picture, because it makes a lot of sense. Here's a parallelogram. Sides are parallel. They're also congruent in length. This height, or this length here is congruent to this length. And obtuse angles congruent to this obtuse. This acute is congruent to this acute. So that means there's a lot of equal parts in this triangle. If I were to, right here, slice my parallelogram and take this triangle and move it here, I'd have a perfect rectangle. Perfect. Look at the length of my rectangle. It's the same length as my base of my parallelogram. Look at the height of my rectangle. It's that same height as the height on my parallelogram. Well, I already know the area of a rectangle. It's base times height, or length times width. So the area of a parallelogram is the same exact area. Area of a parallelogram is base times height. What's the area equal to? Get ready?
Base times height.
Base times height. Go ahead and write that in your notes. Look at me when you're done. Area equals base times height. If you wanted to do this, you could do area of a, and draw a little mini parallelogram. Base times height. Put a big box around it. That's important. Dorian is ready. Mike's ready. Leslie's ready. Corbin, Hadley, Rhett. All right, let's practice. So I've got a parallelogram here. Which one is my height? Is my height 5 or 6? Think. Get ready? 5. So my area should be base times height, which is, remember your units. Get ready?
40 centimeters squared.
40 centimeters squared. So again, we do area equals base times height, or 8 times 5. Your units are centimeters times centimeters, and that's why you've got centimeters squared. So 2 dimensions. Let's do a graphing one. That was review. That was like a course 2, course 1 review, but I know for some it's been a while. So here's something new for course 3. We're going to graph it and dilate it, which is pretty fun. So let's graph. Point A is at 2, 1. Point B is 1, -1. C is at -2, -1. And then D is -1, 1. Let's connect these to make a parallelogram. And let's find the area. Area equals base times height. What is the formula starting with area equals? Get ready?
Base times height.
Good. Start with area. Ready?
Area equals base times height.
Very good. So important, especially when it comes to rice tests. Sometimes they give you the area, and you have to figure out the height. Or they'll give you the area, and you have to figure out the base. So make sure you write down your formula. Our base is 1, 2, 3 units. Our height is 1, 2 units. So base times height is 3 times 2, which is 6 units squared. But here's where we get more fun. Part B of our question says graph the dilation of the parallelogram with a scale factor of 3. What is the area of this image? So I'm going to about a month ago. We talked about dilating about the origin. Let me just clean this picture up a little bit. Back to our anyway. Keep in mind, our dimensions were 3 by 2. If I dilated the dimensions 3 times bigger, I had 3 and a 2. My new one should be 3 times that, should be 9. And my height should be 3 times that, should be 6. But where is it? Let's find out. From the origin to point A, I notice that's 1 unit of length. If I need 3 times that length to find the new A prime, I go up 1 over 2, up 1 over 2, up 1 over 2. My new A prime should be right here. Okay. My B prime, this is 1 unit of length. This would be a second unit, and this would be a third unit. My new B prime should be here. If I did this way, down 1 over 2, down 1 over 2, down 1 over 2, my new C prime should be here. My new D prime is 1 unit, 1 unit, 1 unit. Now that method doesn't work for every student. Some students have a harder time seeing that. So I'm going to show you another way that's maybe easier to see. So here's my new parallelogram. This is possibly easier. We're going to take each coordinate of my original parallelogram. We're going to triple the coordinate. We're going to times it by 3. So my new one would be 6, 3. B prime would be 3 times that, or 3, negative 3. What is my new C prime? Think. Okay, ready?
Negative 6, negative 3.
Good, okay, so we're thinking negative 1 times 3 is just negative 3, good. And then how about this one times it by 3, think? Okay, ready?
Negative 3 times 3.
Good. Now, let's check, did we do it right? 6, 3, over 6, up 3. 3 down 3, over 3, down 3, perfect. Negative 6, negative 3, so left 6, down 3. Negative 3, up 3, negative 3, up 3. They're all in the right spot, so pick whichever way works best for you. If you understand the picture way or that way, do it. What's the area? So area of the new, we'll call it area prime. How about that? We need a distance for our length. Let's count together. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's our length or our base. And then we need a height. Count with me. Ready? 1, 2, 3, 4, 5, 6. Which is 54 units squared. Now, our original area was 6. How many times bigger is our new area? 6 times what? Like, how many times bigger is our new area, Rhett? 9. So that means, wait a minute, didn't we have our scale factor was 3, but we're saying the area was 9 times bigger? Yes, because look. Our dimensions tripled, so really I can fit this same parallelogram right here, right here, right here. I have 3 more of these parallelograms there. 1 more right there, 1 more right there, 1 more right there. I'm not doing it perfect, but you get the idea. There's 9 parallelograms in that. That's why the bigger one is 9 times. Some of you see a relationship. Adam?
Wouldn't it be like, if it was 9 times bigger, then wouldn't it be like base divided by the area?
That's not exactly. It has to do with scale factor. And we're in how many dimensions? 2 dimensions, so it's squared. Whatever your scale factor is, if you square it, that's how many times bigger the area is. Is that what you're going to say, Abby? Kevin, that's what you're going to say? Good. When we get to volume later, we're going to be tripling the scale factor, and then the new volume will be triple. It'll be that scale factor cubed times bigger. Kind of cool. All right, so